Thank you, Lihan, for that nice introduction. So I'm going to talk today about some recent work that I've been doing with my student, Andy Mummery, on, well, interestingly enough, the talk today is going to focus on the orbits themselves of material, really of test particles around black holes. Usually I spend my time with more messy things like disks of gas, and as you heard, with magnetic fields and ongoing complicated thermal processes. But for this talk, I thought it would be interesting to see that there is still useful and exact solutions for the basic orbits of test particles going around black holes, even something as complicated as a Kerr black hole. So before I get too far into the talk, I see a show of hands of how many of you in the audience have actually studied general relativity before? Yeah, not a whole lot. All right. So I hope my talk doesn't fall into this regime where the people who have seen relativity think this is all incredibly obvious and boring. And the ones that haven't seen it find it incomprehensible. But what I'll try to do is sort of set up the problem, at least give you a flavor of what it is. And then I hope that there's at least something new and interesting for everybody in the audience. So the astrophysical setting for this is motivated by accretion disks. And back in the 60s and 70s, when the idea of black holes was still controversial, the only way to study them was to look at what happens to gas when it's in the vicinity of a black hole. And the idea was that if we could understand what those processes would produce, and then if we could observe X-ray sources, say, that by looking at the spectrum and properties like that, that we could learn something about the environment of the gas and hence test whether the ideas of Schwarzschild, I want to say Martin Schwarzschild, but that's his son, Carl Schwarzschild, the originator of the first black hole, and Roy Kerr, to see whether their ideas were correct. But this is an artist's conception of material around a black hole. And now, 50 years onward, we don't need artist conceptions anymore. We can take pictures of black holes, kind of, sort of. It's not very well resolved, as those of you who have followed this understand. But I think there's a pretty good case to be made that what we're looking at here, and this is the M87 image from the EHT, Event Horizon Telescope. And what we're looking at there, that black void in the middle, is not quite the event horizon of a black hole. It's at least the shadow of the black hole where photons are not escaping them or escaping from. So what I want to talk about today is what happens to material basically in disks when it gets very, very close to the black hole. So I'm going to take a step back. The mathematics of this problem requires really the full machinery of general relativity. Now, don't panic too much. General relativity has to look like Newtonian gravity at some point, and you don't have to get very far away from a black hole before it starts to look Newtonian. But when you're very, very close, there are things that happen that simply are ununderstandable, not at all remotely predicted by Newtonian gravity. Work? Yeah. So a black hole really is nothing. It's a vacuum solution. It's hard to learn about black holes because there's nothing there except some kind of an infinite little puncture in the geometry of space-time, whatever that means. And so you have to be incredibly clever to work your way around that and figure out how to learn indirectly about how the geometry of space, and let me be a little more specific, how the geometry of space and how the flow of time are affected by this distortion, or what this distortion really means to the flow of time and to the relationships between the distances in a space. So the space that we're perturbing around, it's already complicated. Even when we haven't done anything, it's already kind of complicated, I think, intuitively, because we live in a four-dimensional space-time. Let's just talk about a four-dimensional space. And it's the space of Minkowski. We'll come to it on the next slide. It's a hyperbolic space. It's a space in which the Pythagorean theorem is not x squared plus y squared plus z squared equals some constant separation, but it's x squared plus y squared minus z squared equals some constant. And it's the minus sign that makes it hard to visualize. And indeed, our conscious sort of copes with it by making that minus sign having another sort of degree of separation. We live in a four-dimensional space, but we experience the separation that comes in with the minus sign. We give it the name time. There's three spaces which I can see simultaneously, but the other separation that we consciously feel is a progression of time from one instant to the next. And that's how we cope with the minus sign. That's why we call it time. It's different. And that's actually the way you would solve it on a computer, by the way. If you were solving an equation that took place in a hyperbolic space, Minkowski space, you would set up the problem the way your consciousness sets up the problem. You would define surfaces, and then you take the next step and you integrate that. And then you take the next step and you integrate that progressively, which is exactly what our consciousness does. If you were solving a problem in ordinary Euclidean space, you wouldn't do it that way. You'd talk about the boundaries here and the boundaries there and the boundary, and then you'd fill it in all at once. You couldn't even begin to do that in the hyperbolic space because the mathematics would blow up. So in some ways, we experience this reality. You're not even aware of it. If I asked you, what's your intuition about what a hyperbolic space would be like? You'd be thinking, well, you're living it. You're experiencing it. You have three-dimensional simultaneity and then progression in time. That's what a hyperbolic space feels like. Now, a black hole screws that all up. It completely collapses the space-time. Black hole is not just a star collapsing, it's bringing the space-time with it. And that's the insight that you can't get with Newtonian theory, but which, and not even back in Schwarzschild's day, they weren't thinking in those terms. Any more than when you say a Newtonian potential is 1 over r, you're not thinking of a mass point. You're saying, well, it's 1 over r up to the surface of the star, and then it changes inside. And certainly that one was Carl Schwarzschild's thinking when he first came up with his solution. It wasn't really what we would call a black hole. It wasn't a singularity. It's just what you have outside the spherical distribution of matter. Now, the most general solution of this vacuum solution to the Einstein equations was found in 1963 by Roy Kerr, and it's one of those amazing solutions. It's just he seems to have pulled it out of the hat. And there's no easy way to describe it. You can try, you can, in retrospect, kind of see where various terms come from, but really it's a magician's act. And what it embodies is both the collapse of material down to a single point, together with all the space-time geometry, and it retains some angular momentum. And in the process, because the geometry is also collapsing as well, the geometry is also spinning. And around a real black hole, not only will it suck you in, but you have to rotate with it as well, because it's bringing the geometry with it. That's what a Kerr black hole does. So let's see some of the mathematics. So there we have what they call the line element. This is what the Pythagorean theorem looks like in a Minkowski space. So let's look at the bottom. Here's dx squared plus dy squared plus dz squared. This is really the same thing, just in spherical coordinates. D omega is the solid angle term. And the minus sign comes in here with the dt. I'm working already sort of for specialists. I put the speed of light equal to 1 here. So this is really c squared d tau squared and c squared dt squared. So everything has dimensions of a length. But it saves writing a little bit if we work in units where the speed of light is 1. And here's the minus sign. This gives the separation between two very, very close points in space and in time. And in general relativity, that combination is invariant. It doesn't change when you mess around with the coordinates, provided that the way you mess around with them is a Lorentz transformation. Lorentz transformations are those particular types of coordinate transformations that leaves this combination of differentials unchanged. Whoops. Have I dropped my? Hang on. Please stand by. Your call is important to us. Okay. So I've made this point now. The space is hyperbolic in structure, and the spheres then have this kind of funny term. And I think I've tried to give you an intuitive feel for understanding what that means, because it's, in some ways, it's common with your experience. Now, here's the exact solution that Carl Schwarzschild came up with in 1915. He takes that Minkowski space, and he says that this interval of time is actually not just dt, but it depends on how close you are near the origin where this singularity is. So R sub s is a quantity called the Schwarzschild radius. It's given by 2 Newton g times the mass that's been swallowed up. And now I put the speed of light back in, divided by c squared. And we also will use just Rg, the gravitational radius, which is gm over c squared. So those will be terms I'll use in this talk. And you can see all kinds of trouble takes place when R is equal to Rs. It goes first to 0, and then it goes negative. And then we have exactly the same term in the denominator for the dr. So the angular part isn't at all affected by the black hole collapsing down, but the radius and the time are. So what this really means is that dt is not your intuitive feeling that time is flowing the same everywhere, but dt really is just what the time would be on a clock infinitely far away from the black hole singularity at r equals 0. And the actual proper time, as it's called, would be this combination with the square root of it multiplied by dt. That's the actual time. It's a little bit like coordinates on the sphere. You can have a change in longitude, but the actual distance is not just the change in longitude, but it's the radius, projected radius, times the change in longitude. That's how you calculate an invariant distance. That could be a little distance near the North Pole, or it could be a much bigger distance at the equator, depends on where you are, and it's the same thing here. What the actual time is, and how it flows, what the time intervals are doing, depends upon where you are. And you notice time will tend to pass more slowly in deep in the well of a deep in the gravitational well. Time goes more slowly on the surface of the Earth than farther away. That's called the gravitational redshift. And then there's also, whoops, also a distortion. Let's see. Yes, then you see there's also a distortion in the space itself. So that was the great contribution that Carl Schwarzschild made, finding the first exact solution to Einstein's field equations of gravity, literally within a month of when Einstein first published his papers. Really a very nice and amazing piece of physics. And some of you may know the story that happened amidst the horrors of World War I. Schwarzschild worked all of this out in the trenches. Amazing, amazing event. So this is what the machinery of general relativity looks like. What about for just any old space-time? Well, we write it this way. That d tau is the same d tau that you just saw. And what we do is we allow for any possibility. So we gather all the coefficients, we call them G mu nu, because that could be time, or phi time, or r phi, any combination of coordinates. And when you see an index here, you sum over it, the usual way. And for something like the Schwarzschild metric or the Minkowski metric, the G mu nu is diagonal. It has entries which are non-zero only when mu and nu are the same. So that's how you interpret that. We define these four velocities as the coordinate dx mu. Mu is simply, could be, think of it, 0, 1, 2, 3, or time x, y, z, or time r, theta, phi, any coordinates you like, completely general, what's called general relativity. And then this guy with the index upstairs has a cousin. We call him the contravariant vector, and there's a covariant vector, which we get by multiplying by G mu nu. And it makes a difference whether you put the indexes up or down. Turns out, pay attention to that. And it also turns out that these quantities, the covariant velocities, they turn out to be constant of motion. So it will turn out, for example, that u phi, that's the angular velocity, d phi, d tau. Notice we use d tau there, not dt. We use the invariant time element, d tau. And u phi, with the phi downstairs, will turn out to be the angular momentum. And u time, u0, will turn out to be the conserved energy. So these are actually, interestingly enough, they have their own little names in general relativity. So you're not supposed to see that immediately from what I've said, but that will turn out to be the case. And so the statement, this statement, minus d tau squared is equal, if I divide both sides by d tau squared, then you can see that the four velocities satisfy, it's kind of like taking a dot product in general coordinates. The four velocities will always, no matter what, add up to -1. Actually, I put the speed of light equal to 1 here, so it's c squared minus c squared. And that's another way to write it. And this is just a reminder, the u0 is dt d tau, so it's a measure of the time dilation. D tau is kind of the time on the clock of somebody moving along through the black hole, what is on his wristwatch. dt is the time interval that an observer would measure at infinity. And here's explicitly what I've said. U phi, for example, is like the angular velocity. U phi is the angular momentum, because you notice r squared is actually g phi phi. So that's the machinery of general relativity. And then life gets even more, a little bit more complicated, the distortions of space and time in Kerr's metric. So we have the same basic formula here. But now when you write it out, well, it starts off okay. This looks an awful lot like Schwarzschild, We have some crazy stuff here, a d phi d tau term, which is a little harder to sort of imagine. That's because of the rotation. It kind of brings phi and t together. And the effect of it is that if you're near a Kerr black hole, when you get close enough, you can't stand still. You have to be dragged around with it. That's what that term does. And then we have the dr, that looks like Schwarzschild. There's a term A, I'll explain that in a moment. And then there's a distortion over here in the azimuthal components where you have two extra terms. So A is a measure of the angular momentum of the black hole. And, oh yeah, I think I have it up here. So basically, A is the physical angular momentum of the black hole, J, divided by the mass of the black hole, and then times C, speed of light, which I haven't written. So basically, the angular momentum of the black hole is J times M A C. A has units of length. And it will turn out that A can vary between one gravitational radius, go to 0, to -1 gravitational radius. It's like the lever arm when you compute angular momentum. Mass times the speed of light times A. And this looks, if you're an expert, if you've studied geometry, I don't know how many people in the audience have, there are bits of this that will remind you of oblate spheroidal coordinates, if you have those on your fingertips. Those A squared terms turn out to be what the geometry looks like outside of general relativity when you work instead of spherical coordinates. In some problems, it's nice to have oblate spheroidal coordinates. A lot of that metric is based on that, with just a few modifications from the dynamics, from the gravitational parts. Now, what's really interesting, this is a descriptive account of what happens when you get very near a Kerr black hole. So you know what, in a Schwarzschild black hole, it's interesting, but rather simple. When you get to the Schwarzschild radius, 2gm over c squared, that's called the event horizon, and that's the point of no return. Roughly speaking, the speed of light, the escape velocity becomes bigger than the speed of light, so you have to keep going into the hole, and there's nothing that can pull you out. And then there's the singularity at the center where the theory in principle breaks down and everything becomes infinite. That's a Schwarzschild black hole. In a Kerr black hole, all right, we have first interesting boundary is called the ergosphere out here. You hit that first. That's the part of space where you have to rotate with the black hole. But you can go into that and out of it. You just have to rotate it. So you can go back, you can go into an ergosphere. It's not the end. And you can get a free ride, and then you come back out. Like Roger Penrose even pointed out in 1969, you can get more energy when you come out. Jumping onto a merry-go-round, zipping up, you can extract energy from a black hole, which was surprising. People didn't think you extract anything. But you can live and play around with the ergosphere. But you better stay away from this. This is the OEH, the outer event horizon. So you cross that, and that's bad. Then you can't go back. You keep on going, and then there is an IEH that you can figure out that thing. That's the inner event horizon. So then you come out, and then there's another ergosphere, but you can't do anything with that. That's almost with no interest. And then instead of having a point-like singularity, you have a ring-like singularity. That was unexpected. Because you can kind of dance right at the center there, and that's okay. but it's the rating that you have to avoid if things become singular. And I have to say, from what I read, the physics of that region, no one is doing any experiment, but it's not well understood. What you find in principle, are you ready? You should be sitting down for this one. The angular velocity, the angular coordinate phi, is you think of as periodic going from 0 to 2 pi, that becomes the time coordinate. Because that's the one that picks up the minus sign. That means you go around, you come back to where you started, and well, you can see all kinds of stuff. So, should I plug and unplug? Infinite tidal forces. Well, the infinite tidal forces would be at the singularity itself, but it's really bad even before it gets to be infinite. Yeah. Okay. That's it. So we have one, but
Yeah, it's bad.
okay. Thank you.
Long in the center of the singularity, we get evenly spread in all directions, so we can actually live.
Well, no, I don't. Not you mean with the ring-like singularity? Well, no, not unless you yourself have spherical symmetry or azimuthal symmetry. Yeah, it would be tough. Yeah. So how do we deal with the mathematics? Let's talk a little bit about that. So what we do to calculate something, you know, if you were to calculate, let me motivate this. Say the distance between 2 points on a sphere. What do we mean by the distance between 2 points on the sphere? We mean the great circle distance. So you can do that by sort of taking a piece of string and putting one piece of the string on Cambridge, and the other piece of the string on New York, and pulling it as tightly as you can, and boop, that'll define a great circle. And that great circle distance is the sort of the minimum distance between 2 points. And the same thing works in general relativity, except that we don't minimize the distance, we maximize the proper time tau. Okay. Did I turn that on? Yeah, when I tap on it, it's there. Can you hear me? I know you can hear me. The electrical people, okay? So the way that you compute orbits is you find the path that maximizes the proper time interval. So what would that mean in sort of practical terms? Well, in practical terms, what it would mean, imagine that I'm here on the Earth, I look at my watch, and it's 8 o'clock, and I want to send a rocket up, and then when it's 8:05, I want to see how much time has elapsed on the rocket if I tape a clock onto the rocket itself. And I take into account all the effects of special and general relativity. So my initial condition is that, as I say, at 8 o'clock, the rocket goes up with a given velocity, and then it has to come back down at 8:05. And of all the infinite possible paths that it could take, the one that has the maximum on its own clock is the right one. So think about that. If you say, oh, well, time goes more slowly deep in the gravitational field, so I want to go up to a large distance very fast, spend all my time there, and then zip back down, be back on time at 8:05. That won't work because you're going so fast that special relativity dilates the time. You're going faster, so not as much time is being put on the clock. On the other hand, if you go too slowly, then you're spending too much time deep in the gravitational well. And so that's not putting much time. So what's the one that maximizes? The one that maximizes is the one that you know. It's the exact one. It goes up, and v squared or v minus at, it slows. That is the actual solution that counterbalances the effect of the gravitational redshift against the special relativity redshift. And that's the one that will maximize the time on the clock on the rocket. And that makes sense when you think about it. Kind of works out the tension between gravitational redshift and special relativity time dilation. And that works always in general relativity, no matter what the space-time geometry is. And in fact, so it turns out to be kind of nice. You can use this combination here, g mu nu, x dot mu, that's like the 4 velocity, that's dx mu d tau, x dot nu, and g mu nu, that's the table of your coefficients in your Pythagorean theorem. And those will depend upon, they won't depend upon x dots, but they'll depend upon coordinates. And you use that as a Lagrangian. And that is this nice simple way to do and find the orbital equations. That works perfectly. Now, when this term, when L is independent of a coordinate, we find immediately from the usual way that the derivative of L with respect to x dot mu is a constant of the motion. So one of the things we find out is that from this, the time equation, the 0 coordinate, u0, g0, 0, must be a constant. That's what this gives us. This term vanishes. And we can call that gamma infinity. I like to call it that because it will turn out that if I'm talking about an orbit that escapes to infinity, and that constant really is the special relativistic Lorentz factor. That's what it is. That's what that constant is at infinity. And if it's not, if it doesn't make it out to infinity, that gamma infinity is still a constant, but then it's less than 1 in the bound orbit. And there is the actual equation of motion that tells me how, it's kind of neat. This tells me the interval, the relationship between the interval between ticks on a clock at infinity versus the ticks on a clock of someone who's not stationary, but moving along undisturbed in an orbit in general relativity. There's how it depends upon R. The other equation that emerges is in Schwarzschild geometry, since the Lagrangian does not depend on phi, is not surprisingly angular momentum conservation. I could call it J. It's actually better to write it as gamma infinity times J, because that's really what the angular momentum, that takes into account whether it's an angular momentum on your watch or on the watch of someone who's, what is the dt, the angular momentum? So the gamma infinity actually sorts that out a little bit better. That's, but J is the kind of introduces the angular momentum constant. And for a photon, I didn't say this, but d tau is 0. For a photon traveling at the speed of light, the universal constant d tau is always 0. So find some other variable to work with. Then the equations that can be done by taking the gamma infinity equal to taking this left over. All right. So we've learned a couple of things, and that's kind of, this is, the time is new, but the fact that angular momentum is conserved, just like the good old days with Newtonian physics. And then the other equation, which you could use the Lagrangian for, but you don't have to. You go back to the original definition. This is an equation for the U's. And this is a perfectly good, not only a geometrical statement, this is a dynamical statement. It tells me how all the U's are related to one another. And so that's a third equation that we can use. You can use the Lagrangian, but it'll turn out to be the same. You get the same result. So here's what happens when you go through that exercise. And just like when you did Newtonian mechanics, you got rid of V phi, wrote it in terms of angular momentum. Then you had an effective potential, and J squared or L squared over 2R squared. That was the centrifugal term, and that was like, you remember it was first year mechanics? Well, all of that comes out. So here is the Newtonian expression of energy conservation, V squared over 2, I'm writing it as a U, because that's the variable, minus GM over R, potential energy, plus J squared over 2R squared. There's Newtonian. Here's what all that exercise gives you. So gamma squared minus 1 over 2, if you think about it, actually is the exact analog. And gamma is very near 1 of the Newtonian energy E. Expand gamma squared in terms of the V squared over C squared, that's in gamma, you see it's exactly the same. This term is exactly the same. This term is exactly the same. This term is, and this combination here is R sub S, a negative R sub S over R. That's the only place general relativity enters into the problem. Kind of changes the sign of the centrifugal term when you're very, very near. This is not Kerr yet. This is just the Schwarzschild black hole. So that's the equation. And that's not too bad. You can do that. Notice it's kind of interesting. The Newtonian, I'll point it out now, is 1 over R squared. Yeah, whereas this has a 1 over R cubed term. And that will make for some interesting differences. So here's just an explicit, this is an exact, just model term I wrote up so you can see qualitatively what's going on. This is all Newtonian, you're used to that. And then what happens when you get right near the Schwarzschild radius in general relativity, boom, the potential plunges downward. So the orbits that are in this region are going to be very interesting and very distinct from the orbits which are in this region. Should we do Kerr? Okay, buckle up. Oh, wait, now I destroyed my drama. Yep. The J is the orbital J in that case, not the black hole J. Yeah, confusing point. So later on when I use it, so the J that you're seeing here now, there'll be no J for the black hole. There'll be A. The A parameter will measure the angular momentum of the black hole. The J is the orbital angular momentum of the particle. There's Kerr. And you're not even supposed to try to understand it. What I just want you to, my point here is that, it's really complicated. Well, we can see here are the Newtonian terms. We don't want to panic too much. I've rewritten this in increasing order, 1 over R, 1 over R squared, 1 over R cubed. So there's the Newtonian terms. And there's the Schwarzschild term that also reappears. And, it's this A squared stuff which starts to become not so intuitive. The main thing that you should take home is even in the Kerr black hole, it's still a 1 over R cubed effective potential. Coefficients are very common, but it's still a 1 over R cubed effective potential. So that doesn't change from the Schwarzschild, even though this is much more complicated looking. All right. Let's talk about circular orbits. So now I'm going to get a little technical, so I'll try to skip over this part. The way that you compute circular orbits is, it's too bad. This is getting, I wonder, I can't really control that, but it's being blocked. the easiest way to do it, you have a U0 in a circular orbit, you have a U5, but you have no UR and no U theta, certainly. And one equation that in a circular orbit you have to satisfy is this one, because every four velocity ever known has to satisfy this, minus c squared in units when you put back the c. But it turns out that there's another very simple equation which embodies the dynamics of having no change in the radial velocity, which turns out to be this: u nu times the partial derivative of g mu nu with respect to r. And this is that expression more generally, but this gives you some idea. So if you take d by dt of u kappa, what you find is that it's proportional to the derivative of the g mu nu with respect to x kappa. And notice this is the covariant form. So I'm not going to prove it, I'm just going to tell you. Textbooks don't do it this way, but it's a good way to do it. And then you see immediately, you see if there's no dependence on x kappa in the g mu nu, that u kappa must be a constant of the motion. And so we do it backwards. Here we know the left side is 0 when I put in r, because it's a circular orbit. And that means this combination on the right must be 0. And this gives me two algebraic equations and two unknowns that I can solve for u0 and u5. And for our present purposes, all you need to know is that you can solve it. That's how you do it. That's how the u0, the time dilation, and the u5, which is both, if you write the phi downstairs, it's the angular momentum. If you write the phi upstairs, it's the angular velocity. And it looks like that. But don't worry, because there will not be a quiz after the talk. And I'm not expecting you to take this all in. It's complicated. The algebra for this gets to be very messy. If it's any consolation, you can take A equals 0 and RG. Remember RG, GM over C squared, the gravitational radius. You can put those equal to 0. And you'll find that U5 really is just Gn over R cubed to the 1/2. That is the angular velocity. And U0, that doesn't really have an analog. It's two different times. But U0 turns out to be an energy here. So it actually makes sense, sort of, at some level. The point is you get explicit, complicated expressions for what the circular velocity is doing as a function of the mass of the black hole and its angular momentum parameter. Oh, yeah. Now, here's something I'm allowed to ask, I think. So you notice the denominator here and here and here, it's always the same. What do you suppose happens when that goes to 0? What does that mean? So that is a quiz. What does it mean to blow up like that? I have enough information to do this problem. That corresponds, remember these are 4 velocities, d something d tau, so it blows up, d tau is 0. No, not a singularity, it's much more nice than a singularity. What thing has d tau equals 0? Yeah, photons. So when that blows up, what is that telling you? That is, where that blows up, that's the orbital radius of a photon. Got that for free. That's exactly what that is. So that's kind of nice. These are the photon circular orbits. And so special cases, when you have a maximally spinning Kerr black hole, so that A is equal to R, that's the motion you can have. The photon radius is the gravitational radius. That also turns out to be the event horizon. Everything in the extreme case of A equals RG, everything happens in one gravitational radius. Photons, event horizon, everything. Schwarzschild, the photon radius, you can see that pretty quickly, is R equals 3G. So 1.5 Schwarzschild photons can orbit. It's not a stable orbit, but it is a circular orbit. Photons fly off one way or the other. And then for a retrograde black hole, the minus sign means the black hole is going in the opposite direction of the orbit. The photon radius goes to 4. So it's somewhere between 1 and 4. So the other thing that comes out of this calculation, look at this diagram. This is the diagram for the angular momentum. So here's Newtonian angular momentum. Remember Newtonian angular? It's really per unit mass. It's the square root of G and R. That's what it is in Keplerian systems. And so that's simple. That's the black line here. And here's the Schwarzschild angular momentum. It goes down. It looks very much like Newtonian, and then whoop, goes up. Let's see how sophisticated you are. Sorry about that. I like the Socratic method. Does anybody here know what happens to a rotation profile where the angular momentum is not increasing outward? Good. You learned at least 2 things here tonight. Then. It's unstable. Can't have it. And the first person who showed this, it's not just for gravitational problems, true for a cup of tea. If the angular momentum is not increasing outwards, you are unstable. And here's a motivation for it. Imagine I have a ring of material, I expand it outwards, keeping its original angular momentum, and try and put it in a place that's farther out. If that original angular momentum is bigger than the orbit at its new location, that is to say, the angular momentum is decreasing outward. If I move that ring out and it has more angular momentum than it should, it'll continue to fly out. If I move that ring out and it has less than the angular momentum it needs to have to remain in that orbit, what will it do? It'll drop back. So it will be stable. So if the angular momentum decreases outward, circular orbits are unstable. So general relativity has a very, very important feature. For the Schwarzschild case, inside of 6 gravitational radii, you can't have a disk, at least not as we know. The orbits are unstable. It gets cut off. And that point is called the ISCO, innermost stable circular orbit. Very interesting. Something when you're trying to understand what disks can tell you about black holes, the disk is going to have at least a different character inside the ISCO. That is the Rayleigh criterion for stability. Well, and this is the argument that I just gave to you verbally, so we can pass on. Oops, sorry. Okay. So that's not, I'm not sure. That's my fault. I think I got my things out of order. That's what I wanted. So there is this complicated U-phi, not just for Schwarzschild, but for any kind of a Kerr metric. And if you want to ask when is that a decreasing function and when is that an increasing function of R, then you have to differentiate it with respect to R, set it equal to 0. And it's not a particularly exciting calculation, but you wind up with an equation for Ri, the innermost stable circular orbit, as a function of A and the gravitational radius. And then you find for the Schwarzschild case, that occurs at 6 gravitational radii, and it ranges between 1 gravitational radius for a Kerr black hole that's spinning around in the same direction, and it could be 9 gravitational radii if the black hole is spinning in the opposite direction of the world. I think it's pretty. The ISCO inside, yes, they don't remain circular orbits. They need to find some other kind of orbit. Yeah, that's exactly right. So let's look at circular orbits from this point of view. This is now back to Newtonian theory. And we have a circular orbit. Here's my effective potential. And here's the energy. And if the energy is up here, I have an elliptical orbit where the orbit goes between these 2 contact points where E equals V. And then for a circular orbit, well, down here, there's a unique place where that happens. So if I write the energy equation this way, and I stick in the E and the J of, that is to say, the energy minus 1/2 Vm over R sub C, that's the location of my circular orbit. The J is the square root of JG MRC. That's the Keplerian total energy and angular momentum. And if I take those values and plug it in here, I find that its right-hand side becomes a perfect square. And that makes sense because what I want is this combination to vanish. And then as you see from the diagram, not only this combination should vanish, but its first derivative should vanish. And if I have a quantity which is a quadratic in 1/r, and I want it to vanish, and I want its first derivative to vanish, that would be an exact square. So it's not a surprise. And you notice the minus sign here, that means the only possible place where I can get a solution is RC equals R. Otherwise, the squared quantity becomes negative. That's impossible. Let's play the same game now with the Kerr effective potential at a point where it is marginally stable. So there, you get something that looks like this. So here, it's okay for it to exist. Growth rate of any instabilities goes to 0 here, and it's impossible to live out here. So here is what this ugly 1/r³ potential looks like. Keep calm and calculate. Circular orbit, ISCO, right? That means the effective potential of its first derivative has to vanish. Marginally stable. That means the next derivative has to vanish. However ugly that cubic is, however ugly, there's only one way. It can be 0, first derivative, and second will vanish. It must be inflated cubic. And you know what? That's just what I've said. Until 2020, that result was not known. And I'll tell you how I found it because my student Andy Mumrian. I mean, we've known a lot about Kerr, but nobody picked up on that. And every problem that tried to do this tried to do it numerically because just look at it. And it turns out what my student did, he wanted to plot that up for the ISCO. So he just calculated painfully what the J and what the, all those constants were, and he put it in it, and then he plotted it up using a standard plotting package, and then he tried another value, and the units he used was R/r. He ran his code, and it kept coming up with the same font every single time. I said, "Why? Something wrong here. It wouldn't change. He convinced himself it was right, but he didn't understand it. And then he went back and he looked at this and he spent about a week plugging everything in, going through a mountain of algebra heroically, because he knew what he was looking for. It's not so easy to spot a cube. You've got to be attuned to the, square is one, a squared, b squared. It's another thing, a cubed, 3a squared b, 6ab, blah, blah, blah. Or rather, 1, 3, 3, 1 combination of the cube is not something. But so he recognized it. He came into my office, and I said, well, I can't believe it. So I said, but we shouldn't have to go through such a laborious calculation to prove this. We went back and forth. We said it's a circle. And I think both of us said it at the same time, and marginally stable. So another derivative had to vanish. And so that's it. But this is very important because this is the universal core velocity for any orbit coming off the ISO for any black hole in the universe. That's really the main result that I wanted to show you in this talk, that it's still possible to do interesting things in general relativity, more or less with pencil and paper. So you see, stay curious. All right, I don't want to take up too much of your time, but just 2 points that I wanted to make. One, notice something I didn't even talk about, but in Newtonian physics, if I tell you that something has, at a location has the energy of a circular orbit and the angular momentum of a circular orbit, it's a circular orbit. That's the end of the story. In general relativity, you can have the energy of a circular orbit and the angular momentum of a circular orbit, and it's not a circular orbit. Because in the case of Newton's perfect square, R equals RC is the only possible solution. But here, as you can see, looking back, I've got the sign rights. I have the sign all okay. So this is a square on the left side, and this is a cube now. If R is less than Ri, that's okay, that's positive. If if R is bigger than Ri, then that's negative. It can't exist out there, as you can see from that diagram. So only orbits inside the ISO. But you keep the energy and the angular momentum as you move inwards. So the next thing, in fact, the final thing I'll do for the talk, since I'm kind of running over a little on time, is to show you what that orbit looks like exactly for the case of a Schwarzschild black hole. So these 2 important points, and the radial forward velocity depends only on the angular momentum indirectly through R sub I, and that's the paper that Andy Memory and I just published in Phys Rev Letters. I couldn't believe it. Let's calculate what the orbit looks like. Well, you know how to do that. You'll have to go from a U sub R, which is a dr d tau, to a dr d phi, and that's just the ratio. If you think about it, UR over U phi, because the d taus cancel out. We know what UR and U phi look like for a Schwarzschild black hole. That's been all sorted out. This turns out to be a relatively easy equation to integrate. This is what the exact orbital solution looks like. Doesn't look very Newtonian, does it? No more epsilon cosine phi in the denominator. 12 over phi squared. You would have expected that. And then those of you who have actually a course in general relativity will remember that you can write down kind of the analog of the Newtonian case as d squared. U is 1 over r plus u, and then gm over j squared. So I have again squared in my formalism, but it's basically the angular momentum. And here's the relativistic term. That's the only difference for a Schwarzschild case. And you tell me, So the book said they give up, they jump off the ship at this point, and they don't even try. And then they do the perihelion. That's all important. But no one just takes a step back and says, can we do this analytically in any regime? Well, yeah, if you try U equals constant plus another constant over 5 squared. And that makes sense because you have a second derivative and a U squared over here. So those terms differentiate 1 over 5 squared. Well, that's an exact solution. There's no textbook in the world that even mentions that, but that's an exact solution. You can do the same thing in Kerr metric, but it's not as pretty. And I'm just going to sort of flash this up. So these are what the orbits look like inside the ISCO, which is out here. As A, you can't even see it. A is going to run from -1 to 1 in this graphic. So now what you see is actually, this is a little complicated because what pops up here is this is the event horizon and things turn around and there I am at 0.9. This is A equals 1. Sorry, it's blocked. And then we go backwards down by returning to the Kerr to the Schwarzschild case. And now we go negative. And now there's the outer event horizon. You notice the orbit is going backwards outside. That's the frame dragging effect of the Kerr metric when I have a retrograde orbit. And then this is all stuff that's happening inside. You'll never see it, but inside the second event horizon. So that's a nice graphic that has everything. It goes a little fast. So I'm sympathetic. It's a little hard to take in all at once. Every single one of those orbits is analytic. Closed form solution. It's not a computer simulation. All right. So I think because time is getting a little bit late, well, I can't resist. Yeah. Just making one more point. When you do accretion problems in the steady state, the quantity 2 pi r sigma ur, that's the mass flux around the ring going in. Sigma is the surface density here. And you notice that we know U sub r in this region, which means we know the surface density of the material flowing in every black hole within the rules of the game for thinking that it remains a disk. That means that there should be a kind of universal surface brightness for the disk from material coming inside the ISCO. Question is, can you see it? It's very close to the black hole. It's very hot, but it doesn't stay there very long. It's an interesting business. Outside the ISCO, the disk is stable and the stuff drips in very, very slowly. Inside, it's a different disk. It goes in and quickly orbits, hit the speed of light, or very near the speed of light, very, very quickly. The question is, can you see anything of that before it disappears? And that's an open research question. Something that, because there are unexplained things about X-ray sources that indicate that you might indeed be seeing something that comes in beyond the ISCO. All right. I will skip over that. That's another pretty solution. Oh, yeah. I'm going to have to skip over that, but there are other classes besides the same techniques that work for the ISCO turns out to be applicable for other orbits, which are inside the ISCO, but not inside the event horizon. That'll have to be a subject of another lecture. And I'm just going to leave you with the final slide that the Kerr metric, it's complicated and it's simple and it's fascinating, and some of it is well understood and some of it is not well understood. It still has lots and lots to teach us, so stay curious. And I've had